you guys know this? Know who this guy is? This guy's Ken Beck. You may know him from XP, TDD, JUnit, 4 Rules of Simple Design. But he also wrote an article a few years ago now where he talks about responsive design, which is an unfortunate name now given that responsive design means something completely different in the UI world. And you also can't find the article anymore because his blog has disappeared and now posts over to Facebook. But in this article, he talks about 2 different design styles, one which he calls the connected style, and the other which he calls the modular style. So in the connected style, everything's joined up. We can quickly get to other components. There's things like global state that let us move around quickly. And then in the modular style, things are pulled apart. There's interfaces and contracts between things. And in the article, Kent contrasts the 2 styles using this chart. So you see the connected style. Here, it's quick to make progress to start with. Because you can get to everything quickly, everything's connected, it's very quick to add new features. It's very cheap to add new features. But as you add more features, the new features interact with the old features, and making a change over here affects something over there. So the cost for adding new features goes up, Kent's suggesting exponentially. And in the modular style, it costs more to get started, but the cost of change is much flatter. And I don't know if you were, I guess you were in Sandra's session earlier, but maybe this point where they cross is an inflection point. I'm not sure. So this cost goes up, and so does anyone recognise this feeling? Has anyone been there? You know, you've been going really fast, and then suddenly you hit the mud. You can't get the thing going, you're stuck. The cost of change is outweighing the costs of building the system in the first place. So there's a quote by Paul Graham, which I find interesting. So your code is your understanding of the problem you're exploring. It's only when you have your code in your head that you really understand the problem. Now this comes from a post by Paul Graham from about 2007, where he called holding a program in one's head. And he compares programming with being a mathematician. Now mathematicians, when they're working on a problem, don't do what we did as kids. They don't sit and scribble and write on paper. They, according to Paul, what they do is they try to create a model in their heads so that they can walk around it like the memory of the house you grew up in. And I think we've all had that feeling where we really know how a system works. But for me, I worry that it sounds a bit like the connected style. You know, features are cheaper to add because we can hold the program in our head at the start. But we've seen what the cost of the connected style is. As we're adding more features, the cognitive load of managing all the dependencies between those connected pieces, connected components, increases rapidly. And we have to remember that making a change here will also make a change over there. So we have this idea that a connected style can get us going quicker, and a modular style will help us improve, will help us keep that cost of change flatter. But how do we reason about how connected our code is? Have any of you heard of Connascence or come across Connascence? Anybody? So I was introduced to Connascence by Jim Wyrick in a talk he gave at the Scottish Rugby Conference in 2010, I think, called The Grand Unified Theory of Software Development. There's various versions of this talk out there. If you can go and find one, watch it, because it's really, really good. Now, in the talk, he introduced Connascence, which was something that a guy called Mailer Page Jones describes in this ancient book, like before, I can't remember what day it was published, but it must be like in the 80s or something, really old. What every programmer should know about object-oriented design. The first half of the book is interesting, but the second half is much more interesting. And in it he talks about connascence. So connascence is a real word, has a Latin root, means the birth of two or more things at the same time, the act of growing together. But for us, in computing, what Mailer Page Jones described it as is two components are connascent if a change in one would require the other to be modified in order to maintain the overall correctness of the system. And connascence gives us a way to reason about the connectedness of our system. Mailer Page Jones wanted a way to evaluate design decisions in an OO system. So he wanted to be able to categorise relationships between components and hint at ways to improve the design. Now, when we talk about component, we could be talking about two lines of code, two methods, two classes, even two separate packages, or even two separate systems communicating across an API. And he describes 9 different levels of connascence. The first 5 are static connascence, and static connascence applies to the code you write, and you assess it from the lexical structure of the code. So it's things that we can see in the code base, our editors can figure it out, we can actively work with it. So connascence of name is about two components must agree on the name of something. Type, components must agree on the type of something. Meaning, components must agree on the interpretation of a value. Algorithm, components must agree on a particular algorithm. And then positions, components must occur in a particular order. Now, these go up in seriousness. So the least serious type of connascence is connascence of name. And connascence of position is something much more actively to be avoided. Past connascence of position, there are 4 more, even worse types of connascence, and these are dynamic connascence. And that's based on the executing code, the running code. So connascence of execution is talking about the order of multiple components. So A has to happen before B. Timing looks much more at, not only does it have to happen in an order, but there is a strict timing issue between the two. So it has to happen a second after, or within 500 milliseconds. Connascence of value is when the values of two components are related. So you could even just think about 2 lines of code. You have an int I and then an I++. So those 2 lines of code are related by connascence of value. Then identity is when multiple components must reference the same entity. So perhaps a queue, or even just an order object where you need, or an email you need to send. So I want to look a bit more at connascence of name. This occurs when things are coupled by sharing a name. Changing the name of something over here requires the change of something else over there. So here we've got a test and a class. So there's a few types of connascence of name on display here. Can anyone tell me some connascence that they can see? Some place where if you change the name of something, you have to change it in another place. The name of the class, yeah. So class card, if we change the name of class card, we have to change the text. Anything else? Name, yeah, the name of the method. So if we change the beats method to be something else, we have to change it in the test as well. There's also the name of the subclass, the superclass. So we're inheriting from Minitest text. If you change the package Minitest or the class test in there, this test would have to change, and probably many, many other tests. So connascence of name is often the weakest form, is the weakest form of connascence. And we don't always have to do much to get rid of it, because we have to have some level of coupling in our systems, otherwise we just have pieces of code sat on their own doing that. But connascence of name is often what you want to try to drive the other forms of connascence down to. So if you have connascence of type or position or algorithm, if you can push it down to connascence of name, that's really valuable. Okay, now connascence of type occurs when two components share knowledge of a type, and changing one affects the other. So take a look at this test. So it's the early stage of the diamond kata, just to explain it a little, which is a kata where you try to print a diamond of letters. And if you ask for an A, you just get an A. If you want a B diamond, you have A, and then the line below has B, then a space, then a B, and the line below has an A, and they're all lined up like a diamond. So you can see here that the A diamond, the first line, so we're just worried about the first line of our diamonds here. The first line is just A, but if we're looking for a B, the first line is A, padded inside with a dash. Okay, so here's an implementation that passes that test. Is there a connascence of type here? Is it a place where two components share knowledge of a type and a change in one affects the other? I've got a version where they're kind of on the same script. Can you see that in the back okay, Scott? Okay, so is there a place where we can see connascence of type there? Parameters and returns, yeah. And the parameters is really important. So if we decide to change our parameter letter from a string to a character, to a chart, we have to change the tests, and then the effects are going to ripple through, and we have to change the implementation as well. And we also have to change not just the parameter that comes in, but these comparison things here and here. And we'll come back to that. So, connascence of meaning. That's where multiple components must agree on the meaning of specific values. So, if you see here, we have these letters. A, return the string here, return a padded A and a different padded A. Those A's all have the same meaning. They're a magic number. They are the start letter. So here, we've gone from connascence of meaning to connascence of name by extracting a constant. Okay, so we've reduced the dependency from three things which are all related, but if we make a change here, we have to make a change here and here, to connascence of name, where, okay, if we make a change here, we have to change here, here, and here, but the meaning has been pulled out. So the type of connectedness is less severe. Okay, so there's also a connascence of algorithm, and this code has connascence of algorithm. So in connascence of algorithm, multiple components must agree on a particular algorithm. So can you see the shared algorithm between parts of this code? Make it a little bit clearer, maybe. So the shared algorithm is each of these lines with a return is calculating the padding. And actually here it's an implicit algorithm, it's just in our heads. We don't know what the real algorithm is. But again, we can move connascence of algorithm to connascence of name by extracting something which does the work for us. And we've reduced not only the connascence of algorithm to connascence of name here, but we've also got rid of the connascence of type, or we've reduced the amount of connascence of type there. So the worst form of static connascence is connascence of position. And connascence of position is where multiple components must agree on the order of values. So we'll go back to our first example, the card test. And can anyone give me the connascence of position that's here? So yes, so in the struct here, this gives us a constructor which gives us an order. So we have to create a card with a rank and then a suit. If we change that around, that ripples through and we have to change that in the test. So how can we get rid of this connascence position? In Ruby, we're lucky that we can create a constructor or a method which uses name parameters. So this then means we can say we expect to have a parameter called rank and a parameter called suit, but we don't care which order they come in. So we can construct it using rank then suit or suit then rank. So a lot of the examples I've shown you have been quite close. The amount of the things that are connected, the things that are connascent, are close to each other. And the thing about connascence is when the distance between the connascent components is small, it doesn't matter if we use stronger forms of connascence, or it matters less. We need to worry about it less. But as the distance between connascent components increases, that's when it's more important to move from stronger to weaker forms of connascence. And if you think about APIs, different systems, maybe REST APIs and things, you can imagine specifying the order that things come in wouldn't be such a great idea. You'd much rather use names, things like a JSON API, for example, rather than just a list of customer description, whatever. So take a look at this. It's a very simple piece of code. We have an available jobs class which generates a list of jobs, which is just an array of tuples, which is the customer and then the description. We have a method which then takes a worker and it does something to assign those jobs to the worker. The connascence here is between here and here. We have to know that customer comes before description. But this is highly local connascence. So we see the connascence position, our spidey sense is probably tingling a little, but we think we can handle it. Getting this code in our head isn't too hard. It's easy to understand the relationship between the code, and if we change it, we know where the problem's going to be, we see the bug, we can fix it. But what if the connascent components are further apart? So now we have a separate class which generates a list of completed jobs, and an invoice clerk which then takes those jobs and generates the invoices. If we changed it here, then seeing the change here is a little harder. And what we strive to do is when we see connascence that's further apart, that maybe makes our spidey sense go up a little. But locality is not the only barometer that we can use to tell. There's also the degree of connascence. So how much connascence there is. If there's a lot of connascence and it's local or fairly local, or if there's a lot of connascence and it's a long way apart, we might want to do something about it. So if our completed jobs was returning a job represented by this array like this, then suddenly we're finding there's a big problem between these two pieces of code. And that's really the time to start thinking that we need to push the level of connascence down, move to one of the lower types of connascence. So we can go from connascence of position to connascence of type by introducing a class to represent our completed job. And then simply all we have to do is return a list of jobs, and we operate on jobs themselves. So connascence gives us these rules to think about. Further apart, two components are use weaker forms of connascence. So when things are close together, note it, but you maybe don't need to fix it straight away. When you have a high degree of connascence, convert to a weaker form of connascence. So, what's good design? Good design is how we arrange our code, how we manage our dependencies. It's how we enable our code to accept change. Change is easy when we can hold everything in our heads. We can understand the connections. But as the system gets bigger, those connections slow us down. We can use connascence as a model to understand how things are connected and what we can do about them. We gives us the rules about locality and degree, and help us judge how much of a problem we have now, and whether we need to fix it. So, next time you get to green, and you're looking to decide what to refactor, maybe try thinking about using Connascence to guide you on what your steps should be. Kevin Rutherford has a series of blog posts and a video where he describes using Connascence to drive each of his refactorings. In fact, I think he works through a project or a kata simply by using Connascence as his guiding principle at each refactoring step, and it's well worth a look. Hasn't worked as well. So, how does this affect the principles we know? We have the solid principles, the dry, law of Demeter. All of those principles are things that people who come before us have observed that help them arrange their code to enable change. So next time you're talking about those and looking at those, I suggest that you try and apply Connascence to them and see how they help you move from strong to weak. So let it go. Instead of getting it all in your head to make you feel like you're in control, try to split things up and make it easy to get a small part you're working on into your head. If we try to optimize our domain so that each piece is quick to get in your head, we can minimize the effects that changes over here have over there. And I think we've got through that really quickly. So, are there any questions? Okay, you can find me here, and those are all photos I've got.